Hello, everybody. So far, in this chapter, we introduced deterministic finite automata. We defined languages that are recognized by DFAs as regular languages, and we tried to analyze the properties of regular languages. And so far, we talked about closure properties. We proved that the union of two regular languages is regular. The intersection of two regular languages is regular. The complement of a regular language is regular. And we try to prove that the reverse of a regular language is regular. And to do so, we looked at a DFA and we tried to reverse it to be a machine that accepts the reverse of the original language. The problem that we had is that this creature is no longer a DFA. In fact, it can do various things at any given point, and therefore we call it non-deterministic finite automata. It can do many things at the same time, and we need to choose which operation to take at any given point in order to reach an accept state. So before we formally define NFAs, let me give you another example of an NFA, and this will allow me to introduce another component of the definition of NFA. So this is a machine with this start state, and you can see that from the same state, there is more than one transition with 0, whereas from this state, there is 0 transitions with 1. So some states have more than one transition, some have 0 transitions. But in addition, we have also this notation of moving with the empty string. So at each state, we have any number of out arrows for some letter sigma, including for the empty string. This will refer to the ability to take steps without reading anything. So whenever there is an epsilon move, it means that you can take this edge even without reading any new symbol from the alphabet. The set of string accepted by this NFA, what is it? Everything that contains a 0. So if you're here and you contain a 0, then you can stay here with 0, 1 and on every one that you see. And the first time you see a 0, you can choose to take an empty string step here, the 0 string, the 0 symbol here, and then stay put. So this is, of course, not the best way to define an NFA for this language, but it helps us demonstrate how NFAs, what's the language of an NFA. And finally, there is two ways of defining NFAs, and here we're going to deviate a little bit from CIPSR. So CIPSR allows a single start state, whereas we will allow multiple start states. And the way to convert NFA with many states to a single state is using this Epsilon transition. So you can define this new state, which is the start state. And now you can take an epsilon transition to each one of the previous start states. And so you can perform whatever computation you could with the many start states. So allowing many start states doesn't increase the power of the machine. You can do the same thing with a single start state. So here is another example of an NFA. And what's the language here? The language here contains two strings. The string that has 1, if you start with this start state and you take a 1, you can accept. and the string 0, 0. You start here and take 0, 0 and accept. So for example, what happens when you look at the string 1, 0? Regardless of which state you start with, there is no path that follows 1, 0. In particular, there is no accepting path that follow 1, 0. So these are the only strings that correspond to accepting path. Now let's define it more formally, still as a 5-tuple, although we are in non-deterministic finite automata, but there will be a slight change in the notion. So a 5-tuple is an FA where Q is still the set of states, sigma is still the finite alphabet. Delta now, the transition function, takes the current state and sigma epsilon, which means sigma when you also augment epsilon to it, you add epsilon to it, meaning that you can take a step with any symbol, but also with the empty state. And now it doesn't give you a single state, it gives you a subset. So 2 to the Q refers to a subset of states, and this subset can be empty or can be large. So these are all the states you can reach when reading Q and the particular symbol. So the Q is a set of all possible subsets of Q, and sigma epsilon is sigma union epsilon. Q0 is the set of start states, so now we allow more than a single state. And F is again the set of accept states. So this is how you specify formally an NFA, and we need to again define what are the languages accepted by the NFA. So a string W is accepted by NFA N if, again, there is a sequence of states, R0 to RK, and we can write W as W1 to WK, where WIs now are not only symbols, are symbols or an empty string, with the following property. The property that R0 is a start state, it's one of the start states, and Rn is one of the accept states, and now Ri plus 1 is a possible transition from Ri on Wi plus 1. So Ri plus 1 is contained in the set of states which is that you can reach from Ri while reading Wi plus 1. So it's in delta Ri Wi plus 1. And this holds for every I from 0 to k minus 1. So this means exactly what we said in words last time. A string is accepted by n if there exists some accepting path from the start state to an accept state. Ln now is the language that is recognized by n, which is exactly the set of all strings that the machine n accepts. And a language L prime is recognized by an NFA, and if L prime is equal L of n. So it's the same terminology we had for DFAs. Again, let's formalize this notion, and we'll do it once in lecture for an NFA. So here is the NFA that we have before. The set of states is Q1, Q2, Q3, Q4. This is the limit of what we can squeeze into the slide. Sigma is 0, 1. Again, it's the binary alphabet. Q0, which is the start state, is contained of two start states. There is Q1 is a start state and Q2 is a start state. The accept state F is Q4. So there is the set is contained only a single accept state. And now let's start defining the transitions. And to define it again for every state and for every symbol, we're going to define a subset of states you can move to. So delta of Q2 and 1, given that you're at Q2 and you read 1, which state you can get to? Well, there is a single state. You can only reach Q4. Delta of Q3 and 1, what can you do? You cannot do anything. With 1, there is no transition, so you reach the empty set of states. Delta of Q1 and 0 contains Q3, and so on and so forth. So now we can ask, is 0, 0 in L of n? Think about it. Well, 0, 0 is easily in L of n because you can walk on 0 from Q1. You can start in Q1, walk on 0 to Q3, and walk on 0 to Q4. How about 0, 1? Well, you would like still to start with Q1. You take a 0 to Q3. But now, how can you take a step with 1? Well, you can directly take a step with 1, but you can first take an epsilon, make an epsilon move from Q3 to Q2, and now take a step with 1. So both of these strings are in L of n. NFAs are generally simpler than DFAs. So for example, this is a DFA that accepts the language which is only 1. Essentially, this is the start state. With 1, you get to an accept state. But now anything else that you'll do, you'll reach a reject state that is a sink. You cannot move out of it. And with a 0 at the beginning, you'll go to this reject state and stay there too. So this is what you need to do with a DFA, but how can you do a simpler NFA? An NFA for the same language is just that. You have a start state. With 1, you move to accept state, and now you don't need to worry about what happens with a 0 here or with a 0 later, because there are no 0 transitions, and therefore anything with a 0 or with more than 1, 1 would not be accepted by the NFA. So it's simpler. So we have here two kinds of computations: a deterministic computation that that has a single path it can take from the start state to either an accept state or reject state. These are the deterministic computations. And we have non-deterministic computations that can be viewed as a tree. At every point, you may have more than a single thing to do, and at some point you get stuck, you have nothing to do. And then in the leaves, you reach accepts or reject. And the question is whether there exists an accepting computation. There could be for every input an accept and a reject computation, but as long as there is an accept one, then you're going to accept. So this looks much richer. And the question is, are these two computations the same or different? So are these computations equally powerful? And when you just look at this picture, it looks like non-deterministic computations are much more powerful. But as many of you know, in fact, these two models of computation can compute the same thing. So as some parting thoughts for this video, when life hands you ambiguity, you can define non-deterministic finite automata. So what we saw here is exactly an example of how good theory works. Good theory reaches an obstacle and turns it into a new notion, and it turns out to be as exciting as anything else we wanted to do. And here, it's the first time we can ask, is verifying easier than computing? So non-deterministic computations can be viewed as a verified guessing. So you have this tree of possibilities. If somebody whispers in your ear, or if you're able to guess, you will guess the right path, the path that leads to the accept state. So you're going to guess it, but then when you follow it, you're verifying that the guess is correct. And now the question is, verifying easier than computing or not? And we'll discuss it in the next video. Thanks. Hello, everybody. So far, we introduced DFAs. We defined the languages that DFAs accept, recognize as regular languages. And we try to prove properties, namely the closure properties. And on the way, we define this notion of NFA, non-deterministic finite automata. And the question that we are dealing with in this video is what's the relation between DFAs and NFAs? And I'm not keeping you in suspense. It turns out that these two models of computations are equivalent in the sense that they recognize the same set of languages. In other words, the set of languages that NFA recognizes are exactly those regular languages, namely the same languages that DFAs can recognize. And this is what we're going to prove in this video. So on one hand, we have DFAs. These are computations with finite memory. And on the other end, we have computations with finite memory that have verified guessing. So non-determinism, the way we want to view it, and it will be even more useful when we'll talk about NP later on, is we want to think about non-determinism as being able to guess and then verify the guesses. So you can imagine that the NFA has some part of it that is whispering in the ear some suggestions. Go there, move here. And a suggestion for which one of the possible things the NFA can do should it do in every given step. And it says, this part says, you know, these are good choices. So you can take these choices, take these guesses, follow them, but at the end, you know for sure. You verify that the guesses were correct by seeing if you reach an accept state or not. And what we show here is that non-determinism doesn't add power for finite automata, which will be different than what we'll see for Turing machines at some point. But we'll discuss what exactly this means at the end of the video. So still, although we define here computation with finite memory and we give it much more power, we don't get anything in return. So one way of viewing it is that this notion of finite memory computation is very robust. And I mentioned it before, and you'll see it in one of your homework assignment. Even changing the model quite a bit will still give you the same computational power. So we want a transformation that takes an NFA as input and gets as output a DFA that recognizes the same language. So this DFA is equivalent to the NFA. The transformation is something that we will call the subset construction for reasons that will become clear very soon. So NFA can do various things in every given step. And now, when you look at it, it's pretty scary because even if at every given state it can do one of two options, then the number of paths it can take is exponential in the size, in the length of the input. And how can this poor DFA monitor what happens in an exponential number of possible paths? So here what we take into account is that in these computations, we don't really care which path you've taken so far, because DFAs and NFAs only care about the current state. The current state tells you everything you need to know for what happened so far. So instead of monitoring all the different paths you can take, which is exponential in the length of your input, we will only monitor all the possible states you could have reached. This is exponential, but exponential just in the number of states. And the number of states, this is an NFA, it's a constant. So exponential in a constant is still a constant. So that's the kind of the idea. To learn if an NFA accepts, we could do computation in parallel, but not in parallel over all paths, but just in parallel over all states. So what we will maintain is the set of all possible states that can be reached by the NFA on the prefix of the input we saw so far. The idea is to define the set of states, Q prime, of the DFA to be the power set 2 to the Q. So all possible subsets of states in Q. I hope this is clear. This is where I'll ask you for questions, but I can't. So we have the first ingredient in this subset construction. The most important ingredient is that Q prime is 2 to the Q. The rest will more or less follow. There will be one natural thing to do at every given point with some subtle technicalities, but not too subtle. So what is the transition function? This is the other interesting thing. Right, so let's see that Q translates to Q prime. The alphabet doesn't change. The DFA runs computation on the same alphabet as the NFA. So the next thing that does change is the transition function from delta to delta prime. And delta prime takes an element in Q prime and an alphabet symbol and gives you the next state in Q prime. The way we want to define it is to take the current state R, which is an element in Q prime. So R is an element in Q prime, which is a subset of states in Q. So R is a subset of Q. And these are all the states you could have reached so far. Now, from each one of them, you're going to ask, what can I reach now that I'm taking a sigma step? So we're going to take the union over states R in R of the things you could reach from R with the step while reading sigma. So what are these things? This is where we take into account the transition function of the NFA. So the NFA-N tells us that on state R, with reading symbol sigma, you reach the states, which can be 0 or more states, specified by delta of R and sigma. So delta of R and sigma is a subset of states. And these are the states you can reach in the NFA from R reading sigma. But we're not done, because remember these epsilon states. So we need to see not only what states you can take by taking sigma, what states you can reach by reading sigma, but then what you can reach by taking 0 or more epsilon transitions. So this part of taking 0 or more epsilon transition, we will refer to as the epsilon closure. So let's look at the definition of the epsilon closure. It's just what I said. So for every subset S, like this subset, delta of R sigma is a subset S, the epsilon closure of S, that we denote epsilon of S, are all the states reachable from some S in S, some state in S, by taking 0 or more epsilon transitions. So for example, which states are for sure in the epsilon transition of S? Yes, I hope that's what you've been yelling. S is always contained in the epsilon transition, epsilon closure of S, because each state in S can be reached from itself by taking 0 epsilon transitions. We will check this notion and see an example very soon. Now, once we define the transition function of this DFA, we can define the start state and the accept state. The start state, Q0 prime, is the epsilon closure of all the start states of the NFA. So Q0 is all the states you can start with in the NFA, and you take their epsilon closure. And finally, accept state, F prime, are all the subsets that contain some accept state of the NFA. So remember that an NFA can accept a string if there is some path to an accepting state. There are paths perhaps for other states that are rejecting, but it's enough that there is one path to an accepting state. What we've done, we monitored all the states we can reach, and if one of them is accept, then this means that we can accept, because there is a path to an accept state. So that's the construction, the subset construction, and what we'll do in the remaining of this video is give you an example of applying it, and that's something you should be able to do by yourself. So before we look at applying the construction, let's start by exercising the epsilon closure. So look at this NFA, and we'll look at the epsilon closure of each one of the states, Q0, Q1, and Q2. And the epsilon closure is defined for subsets, not only for individual, but it will be the union of this. So if we want the epsilon closure of the set containing Q0 and Q1, it will be the union of the epsilon closure of Q0 and the epsilon closure of Q1. So what's the epsilon closure of Q0? Well, from Q0, you can reach itself taking 0 epsilon transitions, but we see here an epsilon transition, so you can also reach Q1. And Q1 also has an epsilon transition to Q2. So in fact, from Q0, you can reach all the states with epsilon transition. So the epsilon closure of the set containing Q0 is Q0, Q1, and Q2. Similarly, the epsilon closure of Q1 is Q1 itself and Q2. But the epsilon closure of Q2, the set containing Q2 is Q2 itself only, because there is no epsilon transition starting from Q2. So now that we're experts in epsilon closures, let's apply the transition, the subset construction to this NFA on the left, which is N. Now the equivalent NFA has all the subsets. So it has 8 states, which are all the subsets of 1, 2, 3. And one thing we could have done is just draw these 8 new nodes and calculate all the transitions that are possible from all of these nodes. So 8 nodes, and we have 2 alphabet symbols, so we can ask 16 questions here. And we'll do a trick that will be useful for us and will be useful later for you in exercises. which is not to build everything, but to build everything that you can reach from the start vertex. So what we'll do is first realize what is the start vertex of the DFA, and then we'll start growing the DFA by checking transitions, and we'll only draw states that we reach. And states we don't reach, we don't need to draw them, and we don't need to calculate what are the transitions. So the question is, what is the start state of M? It is the epsilon closure of the set of starting states at N. Now N has a single start state, so it's the epsilon closure of 1. Let you think for a second, what is the epsilon closure of 1? So let's see, definitely 1 itself, you can reach it with 0 epsilon transitions, but you also have an epsilon transition to 3, and that's it. There are no more epsilon transitions, so the epsilon closure of 1 is 1, 3, and this is the start state of the DFA. What else can we say about this state? Well, we can say that since this state includes 1, then it is also an accept state. It is start state, but it is only also an accept state. All the sets that include the accept state of N are accept states. So 1, 3 is the start state, and it is also an accept state. Let's see where do you reach with an A transition from 1, 3. So let's look. From 1, you have no transition, no A transition, so let's move to 3. From 3, you have an A transition to 1. So it looks like from 1, 3, with an A transition, you can only reach 1, but we need to stop for a second and realize that the construction told us not only to find those that can be reached by reading an A, but also the epsilon closure of that. So from 1, 3, you don't reach 1, but you reach the epsilon closure of 1. The epsilon closure of 1, we already calculated, is 1, 3. So A from 1, 3 is a self loop. Let's look at B. From 1, 3, where can you reach on B? From 1, you can reach 2. From, and only through, from 3, there is no B transition, so you cannot reach anything else. So from 1, 3, you can reach 2 with the B transition, and you need to take the epsilon closure, but the epsilon closure of 2 is just 2, because 2 doesn't have any epsilon transitions. Now from 2, let's ask what is the A transition. So where can you reach from 2 with A? You can reach itself, there is a self loop, you can reach 3. So, so you have from 2, you can reach the set to 3. And now you need to take the epsilon closure of 2, 3, but it is just 2, 3 itself. Again, no epsilon transitions. What about B? Where can you reach from with B? So from 2, 3 on B, you can reach 3, and that's it. So you have a B transition to 3. Now we have 2 states to follow their transitions. So let's look at 2, 3. Where do you reach with an A transition? So from 2, you can reach itself, you can reach 3. From 3, you can reach 1. So we already saw that you can reach 1, 2, 3, and the epsilon closure of 1, 2, 3 is just 1, 2, 3. You cannot grow it anymore. It's just maximal. What can we say about this state? This state contains 1, and this is also, therefore, an accept state. Okay. What happens when you take an A transition here from 1 to 3? Well, from 2 you can reach itself, you can reach 3. From 3 you can reach 1, and so this is a self loop. So 1 to 3 on A is a self loop. How about a B? From 2 on a B you can reach 3. From 1 on a B you can reach 2. And that's it. And there are no epsilon closure. The epsilon closure is the same. So a B would bring you back to 3. And with a B from 2, 3, you can reach 3. Because there is no transition from 3 labeled B. And from 2, you can reach 3. And now we need to still define the transitions from 3. With A, from 3 you reach 1, and the epsilon closure of 1 is 1, 3. And how about B? With B, from 3 you reach nothing, right? There is no B transition, and the epsilon closure of the empty set is empty, so this is the empty set. Once you're in the empty set, then you stay put. There is nothing more that you can do. And so we reached at the end, we calculated all of the transitions, and we reached 6 of the 8 states. 2 states, 1 and 1, 2 are just not reachable. So no point in drawing them and calculating them. So that's the entire construction. I hope I was clear. We can go over it in the live meeting again. So before we leave, let's kind of contemplate on what we saw. We saw that NFA equals DFA. And we can ask, does it mean that non-determinism is free for finite automata? It's free in the sense that you cannot recognize with the non-deterministic finite automata any language that is not regular. But the construction itself wasn't free. The number of states grew exponentially. So if we think about it as an actual computational device, then yeah, we can have another constant size device, but it will be significantly larger. So if you have an DFA, an NFA with 10 states, you may reach DFA with 1,000 states. If you have one with 50 states, then it is already 2 to the 50. So it's not for free, but it does tell us that constant memory computations are very robust. Different definitions give us the same family of languages.